still active in primordial black holes is Bernard Carr, who is a student of Stephen Hawking. And Bernard Carr produced and is still working on producing compilation of observational limits to the abundance of primordial black holes. What fraction of dark matter can primordial black holes make as a function of the mass of the black hole? So my take on primordial black holes, so people tend to be very polarized. I'm not a believer nor a hater. I think it's a very interesting problem, and it should be, given the same rigor as you would give to any dark matter candidate, because we still don't have any, dark matter candidate that we know for sure is dark matter. And even if primordial black holes are not the dark matter, they can inform us about the initial conditions in the universe. Even upper limits can give us some kind of information about initial conditions. So to put this in a bit of a more modern context, in the most standard picture that we have of inflation, we expect that the primordial curvature perturbation should be roughly flat over 15 to 25 decades. What has been actually measured is only something like 3 decades by CMB, anisotropies, and large-scale structure. But on smaller scales, we have some upper limits from self-damping, which set some upper limits on how large was the amplitude of small-scale perturbations. But mostly, these very small scales are not directly observed and are unknown. And so who knows what kind of unknown physics could hide there. And so primordial black holes are some way, although it's not very, it's a challenging way to extract constraints of the primordial power spectrum from primordial black holes, but it's some way to probe some window onto these very small scales in the early years. All right. And this is a modern, I took this from this paper by Satropolito, Koves, and Kamikoski, which is some compilation. I think it's incomplete. I think, Avi, your limits should be here.
Everything is ruled out.
Everything is ruled out.
No, I mean, there is, the dark matter cannot be promoted.
Right. So, except in this range. And so I'll go to this point. So thank you for making this point. I think even if, so this is typically what I hear, that everything is ruled out, so let's stop thinking about it. Why do I think it's so interesting to think about it and to try and set stronger limits? Because some people will always come up with some crazy models of the extended mass function of primordial black holes. In fact, there's no reason to expect that primordial black holes should all have exactly the same mass. And so, for example, this is a paper by Bernard Carr, Garcia Bellido, where they fold in some actual calculation of the equation of state through QCD and electroweak phase transition. They still have some large primordial power fluctuation, but here, what you see here are the manifestations of the changes in the equation of state of the QCD phase transition. Yes?
So it's suggestive to say that low mass black holes are identified exactly with primordial or early black holes, but has any progress been made in thinking of later procedure that could form extremely low mass black holes, even so late that they may not have even completely evaporated or may even...
So you mean like in the recent universe,
yes,
forming low mass black holes but not out of stars?
Yeah. So is it certainly primordial black holes, there's no conceivable way of making them from anything other than primordial density perturbations, or...
You would have to talk to stellar physicists, but my understanding is that it's very difficult to form them out of stars if they're low mass. But
open
yeah,
any process that would make
you can probably think of one, but I haven't personally. But yeah, there might. I don't know. My answer is I don't know, but yeah, there could be something. But indeed, like if in this very low mass, so far no one has come up with any, I think, scenario to form very low mass black holes. Just something.
So if you have like dark matter self-interaction physics, you can change the dark center sector mass by having a dark electron, and you can have, black holes of lower masses if you want to think.
what masses?
Whatever you want, just so great.
But you need the dark matter fluctuations, these large fluctuations.
So these would be dark matter that forms dark stars that collapse.
Yeah, but in order for them to collapse,
yeah, it will form dark stars the same way regular bearings form stars. So don't put John let's stay as a bigger ones.
Okay.
But then the traffic is
So anyway, so the point of this, to go back to your point, Andy, is that you could have, it might look like it's ruled out everywhere, but I think it's still interesting to look at how low a fraction you can have, because you could probe the tails of some extended mass
Just a
distribution.
comment about the LIGO sources. Some people suggest that the LIGO sources are primordial. The best argument against it, in my view, is that there is a cutoff at 40 solar masses
Yeah.
in the black hole mass function
Yeah.
detected by LIGO. From stellar evolution, we can understand that.
Right, yeah. No, I agree. I don't think LIGO shows that they're primordial. I'll get back to this. Okay. So what I've worked on is specifically this mass range around few to 1,000 solar masses, where I think that cosmic microwave background and gravitational waves are likely the most sensitive and clean-ish, as you'll see, probes of primordial black holes. So in the next few minutes, I will just explain briefly what's the physics underlying these bounds on the CMB and hear from LIGO. So first, the CMB. So suppose that the dark matter is made of black holes instead of black holes. Those are my artist rendition of black holes. Those black holes are in some primordial gas. Now black holes, when they see gas, they like to accrete it. So there will be some accretion of gas onto these black holes. The way we've computed this is by using some modified, simple but modified Bondi-Heuer-Littleton accretion, and modified to account for the fact that this accretion takes place in a universe that has a lot of photons, which exert a drag onto the accreting material, and also cool down the gas through quantum cooling. Now, part of the accreted rest mass will be re-radiated. So the next step of the calculation is to figure out what is the efficiency of radiation, what is the luminosity of these accreting black holes. So here what we've assumed, we've tried to assume the minimum plausible emission, but yet computable from first principles, so we could set the most conservative possible upper limits. So this is likely very low compared to what you might expect, but this is at least something we could compute from first principles. So from first principles, we estimated luminosity, assuming it comes from free radiation from the gas, which is heated up and ionized as it accretes onto the black hole. The next step is given some luminosity per black hole, you can compute a rate at which the energy is injected into the plasma. From this, you need to figure out the rate at which the energy is deposited into the plasma. It doesn't have to be equal. It doesn't have to be deposited on the spot. And then from this, you can figure out how much these, so now we've zoomed in, those are my little hydrogen atoms, and so the additional energy can ionize hydrogen beyond its normal ionization state. And so if you remember, as I showed you before, if you ionize hydrogen beyond its normal ionization state, you will change the CMB anisotropy power spectra. So this is the fractional change in the free electron fraction as a function of redshift for different black hole masses and abundances, and this leads to some changes in the temperature and polarization power spectrum. And for those who've thought about the CMB a little bit, this is qualitatively similar to an optical depth to reionization, in the sense that it suppresses anisotropies on small scales and also enhances polarization on large scales because of rescattering among parastates. We're not the first ones to look at this, but I think this is one of the most detailed works on this. So, in fact, Cole-Miller in 2000 was the first to suggest that CMB anisotropies could be a probe of accreting primordial black holes.
So in your paper, you only belong to 10,000 solar mass. What if the mass of the black hole is larger?
Yes, so I stop here around 10,000 because beyond this, so we have lots of course, assumptions. One of the assumptions that breaks down is the quasi-stationary assumption. So if it's beyond, there will be some effect, and I'm hoping to find a student who will be willing to compute this, but you'll have to just solve for the full time-dependent accretion. That's all. Yes?
Listen, you're very modest because if I remember correctly, there was a mistake in the previous work by orders of magnitude.
I mean,
and you
so,
corrected it.
Yes. There was some mistake. The one mistake, so there was a mistake on spectral distortions. There was a typo in the paper. I'm not sure if it was the mistake. There was a mistake in the treatment of relative velocities, which I'll get to in a minute. But then otherwise, the rest I wouldn't call mistakes, but rather assumptions. And the assumptions were that the accretion is much more efficient. So some efficiency parameter was put in by hand, and I prefer knowing where my efficiency comes in. And I don't think one can just infer how black holes would accrete at redshift 1000, given how the few systems we see accrete in the present universe. But you could probably, and I'd love to talk, if whoever wants to talk about this, you could probably make these limits much stronger if you were more confident in the physics of accretion. So one thing that I'm excited about, and I think could set stronger limits, is to look beyond the power spectrum of the cylinder. So Julian kindly made this plot for me in a few hours. So this is a 2D plot of the relative velocity between dark matter and baryons. Dark matter, in this case, is primordial black holes, or in part primordial black holes. Those are very, very large scales. So it doesn't matter on these scales whether the dark matter is made of black holes or what. Those are just obtained from linear perturbation theory. And so now if I take a simple Monty-Hoyle-Littleton accretion, so the accretion rate is inversely proportional to some effective velocity to the cube, and then for free radiation you have luminosity equals m dot squared, you'll see that the luminosity is in fact highly inhomogeneous and is going to be highly peaked in regions where you have low relative velocities. So the picture, so what we did in the paper is to just take the average, the spatial average of this quantity to compute the energy injection. But this is assuming effectively that this energy which is injected locally is quickly uniform, distributed in a uniform way. In practice, and something that I'm working on with student